Hey everyone, Chang here and welcome to my channel. Now for today's video, I want to break down the structure of a math textbook. The reason for that is not because I'm saying everyone needs to read the math textbook from page 1 all the way to the back cover. That's not the case at all. But guess what? When we are studying math, there's always going to be important information, important definitions, important concepts that we need to grasp. Since we have a limited amount of bandwidth on what we can actually memorize and recall right away, we have to be able to go into a math textbook and grab the necessary information very quickly. So, by understanding the structure of a math textbook, based on the nature of the information, we know exactly what to look for. What's the difference between a definition and a theorem? Or an axiom, or corollaries. If we know those basic nature, then we can immediately look, all right, what I need is a definition. I can ignore axioms, I can ignore theorems, corollaries whatsoever. If I just skim through all the definition, most likely what I need is going to be there. Just by understanding this, it'll save you a lot of times and frustration when you're looking for the necessary information. So let's begin. Alright, so for our first thing, we're going to talk about definition. I want to say definition is this overarching sort of umbrella, right? It incorporates two different things. The first one are theorems, and the second one are axioms. The whole point of definition is that it is basically introducing a vocabulary with precise condition. So that means you have to read it thoroughly, because unlike reading a standard novel or, I don't know, any kind of non-fiction book, reading a math textbook, almost every other word plays a special role for you to understand what that word means, what that vocabulary entails. So let's look at this, for example. First and foremost, definition. It could be axioms or theorems, and they have to be very precise. Okay? So they are always precise. So I've introduced, or I'm written down two different definitions. And this is from a textbook that's actually a while back, and it's actually pretty technical. I think in the 1950s, 1960s. So the first one, definition 1.1, to subtract b from a means to add negative b to a, right? That seems kind of weird, but actually it gives us a lot more information under the surface. When we're talking about subtraction, right, if we're saying that that just means you're adding these two together, all of a sudden stuff like commutative property, associative property, distributive property, all those things actually work, because guess what? When you are first introduced to subtraction, you really can't use commutative property or associative property, because, well, let's just say, for example, 3 minus 2 and 2 minus 3 are two completely different numbers. But if we have a definition that subtraction is just the adding of these two, then since we're just adding these two, all of a sudden we can switch it around. A plus negative b is the same as negative b plus a, and vice versa, right? So that's the, I guess you could say, the pinnacle precision of definition. Let's look at the second one really quickly. A positive integer greater than 1 is a prime number if it cannot be expressed as the product of two integers except for itself and 1. So there's several things that we have to pay attention to, right? If we're talking about a prime number, first and foremost, we need it to be positive. That means any negative number doesn't count. 0 does not count. And we also understand that it is integers. So they're all whole numbers. They're saying positive integers, basically all positive whole numbers, right? Greater than 1 is a prime number if it cannot be expressed as a product of two integers again, right? So you're not working with decimals, you're not working with fractions per se, you're working with whole numbers, except, well, basically the product of two integers except itself and 1. So there's no smaller number. It has to be that specific number and 1 itself, right? Notice all these key details just to define what a prime number is. That's the purpose of definitions. Alright, so for our next one, we're talking about axioms. Axioms, once again, is one of the two that definitions are based off of. Now, the difference between axioms and theorem is that axioms are basically statements that are generally agreed upon. Those are the rules that no one's going to contest against. We just accept it and use it as building blocks for more complicated results, formulas, theorems, so on and so forth, right? And usually axioms are based on what we observe, or, well, I mean, what seems to make absolute sense. So basically statements that are not contested. Statements let's just say accept it as facts. So these are examples of axioms based on that same textbook. The first one is fairly simple. To each pair of real numbers a and b, there is a unique sum a plus b and a unique product a times b. So what is this saying? This axiom is saying that if you add any two numbers, right, two specific numbers, there's only gonna be that one result that equals that addition. So if you add 3 and 2, there's only gonna be that one result, which is 5. That is your sum. It's not gonna all of a sudden be 6. It's not gonna all of a sudden be 10, 20, negative 100, right? That's what this is saying, right? And once again, it's for addition and multiplication. So when you multiply two numbers, you have 5 times 3, for example, you know it's gonna be 15. It's not gonna all of a sudden become 16 in some special case or whatsoever. It's gonna be 15 no matter what. So pointing out, I guess you could say sometimes the obvious, something that we just accepted as facts, right? That's what axioms are. So that's the first one. It's just saying that every time you add two numbers together, that end result is always gonna be that end result. There's no if, ands, or but. There's no in a case or a condition. Doesn't work that way. That's always gonna be the answer. Same when if you multiply them. The second one is actually quite interesting because guess what? This is the one that can be used as a definition as well. So axiom 6a is saying that corresponding to each real number a, there is a unique real number minus a, or in this notation, obeying the law that a plus negative a equals 0. And the number negative a is actually called negative. So this itself is the introduction of negative numbers. And it defines what negative numbers are. Negative numbers basically has that minus sign in front of it such that when you add it with its corresponding numbers, it gives you the end result is 0. So there's a lot of things we can unpack from this. There's the fact that it has to be unique, right? It's not going to be two very different negative numbers that add to the same number and give you 0. So for example, if you have 2, the only number that you can add to 2 to make it 0 is negative 2. It's not going to all of a sudden be negative 2 and another different number, right? If that other number adds with 2 to become 0, guess what? They have to be the same because they're unique, right? So this is an axiom that introduces the definition of negative number and gives you the condition of what a negative number is. So these are axioms. So of course you guys can guess. The next one I'm going to talk about are theorems. Alright, so of course now we're talking about theorems. So theorems is actually very similar to axioms except for one key difference. The key difference is that axioms are accepted as fact. No one is arguing against it. Theorems, however, you actually have to prove that specific statement. So it's not just something, I say this is a theorem, there we go. No, prove to me that that is the end result. So that's the key difference. Now, in order to prove theorems, there's two ways to go about it. It's usually going to relate to either the axioms or it's going to be related to some, I guess you could say, creative manipulation of previous theorems that you've proven before. So let's look at this really quickly. So theorems is statements that need to be proven. Let's just write that as a crude definition that needs to be proven. So this one right here, actually, based on the textbook, is a theorem, and it makes sense because guess what? This is not a part of the axioms, it's not necessarily a part of the definitions, but you can actually prove this. So how would you prove this? What it's saying is that negative of a negative a is the same as a. Now, in order to prove this, their proof is actually very amazing, quite simplistic, but it makes absolute sense. The key is actually that axiom 6a that I introduced in the previous section. So let's look at this. We know that based on axiom 6a, that if we have a plus negative a, that equals 0. Okay, that's based on the definition of negative numbers or axiom 6a. Okay, now keep in mind that we can also say, for example, negative a plus negative a is equal to 0. Why? Because once again, axiom 6a. Okay, the reason for that is because guess what? This negative is saying that it's negative of this guy, Well, negative of this guy, by definition of a negative number, when you add them together, they should equal 0. Now, what else can we do? There was a key word that I pointed out when I was introducing Axiom 6a. The idea of it having to be unique. That negative number must be unique. So that if, for example, in this case, a plus negative a equals 0 and negative of negative a plus negative a equals 0, these guys are the same. That's cool. The end result, of course, is the same. So, by Axiom 6a, just the fact that it has to be unique, that means these two must be the same as well. So, that means a must equal negative of a negative a. And just like that, this statement, this theorem 1.1 is proven using based on axioms only. And of course, the more complicated it is, it's probably not just going to be based on axioms. It's going to be based on axioms and previous theorems and definitions and so on and so forth. But that's how theorem differs from basically axioms. Alright, so our final segment is talking about corollaries. Now here's the thing about corollaries. Certain math textbooks will use the word corollaries, others will not. Others will just use the word theorem. Now, what's the difference between corollaries and theorems? Well, corollaries are still theorems. However, there's a caveat. Corollaries are usually theorems based on another theorem. Either it is an alternative result or the end result of another theorem that seems amazing, that has some use, that's why we focus on it, we call it corollaries. Or it's a byproduct of when you're trying to prove the previous theorems. Going through the proof, all of a sudden some interesting result happened. We're going to save that for later. That is also known as corollaries. So other than that, corollaries are just theorems. So theorems, but closely related to the previous one. So theorems closely related to previous. Okay, cool. So, here's the thing. I'm going to show you guys an example. First and foremost, we have theorem 1.2. A times 0 equals 0. Now, there are certain textbooks that will argue that this result is an axiom. Well, for the specific textbook that I'm referring to, they call it a theorem. Doesn't really matter that much. I'm only putting it there because I'm going to use that to prove theorem 1.3. And while I'm proving theorem 1.3, we will realize that actually another result occurs, and that is what a corollary is. Right? So for example, theorem 1.2, a times 0 equals 0. Great. Wonderful. We're actually going to use a theorem to prove a theorem. So hence, why I say certain theorems are proven by axioms, certain theorems are proven by previous theorems. So that's what we're going to do. So theorem 1.3, a times negative b is the same as negative ab. Well, the proof is fairly simple. First and foremost, we start off with 0. 0 equals a times 0. That is based on theorem 1.2, right? Well, based on axiom 6a, we can actually write a times b plus negative b. Okay, and of course we have the distributive property, which is a different axiom. I didn't write it all out, but it's an agreed upon axiom that allows us to write a times b plus a times negative b. We also know 0 equals ab plus negative ab. Just by the definition of negative numbers, right? This negative ab is the negative numbers of ab. So by axiom 6a, or the definition of negative number, these guys add together to become 0. Well, remember, axiom 6a also says that it has to be unique. So all of a sudden, this right here, a times negative b plus ab equals 0, and this right here, right, negative ab plus ab equals 0. That means these two, since it has to be unique, are equal. So that proves this specific statement, right? This is proven. Great. Now, where does the corollary come in? Well, I'm going to say corollary a times negative b is the same as negative a times b. Now, how is that a corollary? Where did it come from? Well, this whole proof, what if I switched it around? What if instead of 0 equals a times 0, I say 0 equals b times 0. And then all of a sudden switch things around. We also have our commutative property with multiplication. This is where the corollary comes in, right? It's just a byproduct. As I was proving this, oh look, it's interesting. So we have a times negative b, but guess what? If I change this around just a little bit and go through the proof again, all of a sudden I'm saying that negative a times b. So that result is the same. Therefore, these two must be the same. A times negative b is equal to negative a times b, which is great. So that means all three of them are the same. So instead of just a times negative b equals negative ab, we can also add, based on the corollary, right? That equals negative a times b. That's how corollaries are formed, or how they are closely related to the parent or the previous theorems. All right, so here we are at the end of the video. Now, I drew this very lovely structure, right, to show you guys basically the overarching theme. Definition is either based on axiom or theorems, right? It's just defining a specific vocabulary word with conditions. So if you're just trying to remember what a specific vocabulary word means, look up definitions. That's all you're looking up. You're going to skim through the entire book. If it says definition, or usually it might not say definition, it just has the bold. It's like, all right, that's probably what I need to look at. Then you have your axioms. These are the agreed upon rule, guidelines, accepted facts, basically. So if it's one of those, then, well, there it is. But usually these are very limited, so it's actually probably a good idea just to memorize it. For example, the common acceptance of algebra is that there are 7 axioms that if you could just memorize, then you really don't have to look it up. Now, you have your theorems and corollaries. Now, here's the thing. Once again, theorems are proven results based on either previous theorems or axioms. And corollaries are just theorems and very closely related to each other. So if you're looking for a result that you realize is probably the offspring, the byproduct of a bigger theorem, then you're looking up words, corollaries, right? You're looking through corollaries. Once you see that, all right, that's probably it. Theorems, once again, if it's a result that you feel like it's proven, my instructor proved it before, I've seen it somewhere, then that's probably where you're looking for, right? So there it is. That's the general structure. Once again, I'm not expecting you guys to read a math textbook. I've tried. It's fun at times depending on the textbook, but 9 out of 10 times not really, right? Usually I just want to get my information and get out. So knowing the structure, this definitely helps speed up the process. Hopefully you find this video helpful. If so, please like, comment, and subscribe. Thank you for watching. I will see you in the next video.